In this set of problems, we're asked to talk about a specific position vector in the plane. R of t is ti plus the natural log of cosecant j. T is between 0 and pi. And we're supposed to, in question number 1, find the curvature as a function on t, and then find the frenet frame, the vectors big T, big N, and big B. So, my position function, R of t, the I component is t, and the j component is cosecant t. I'm asked to find the curvature. So the first thing I kind of need to think about is what I need to know to find curvature. Well, one of the calculation formulas for curvature is 1 over speed times the magnitude of the derivative of big dt dt. So I need to calculate these things. I need to know speed, which means I need to find velocity. I need to calculate the unit tangent vector so I can find its derivative and calculate that derivative's magnitude. So to start off, let's find the velocity vector. Derivative of t is 1. The derivative of the natural log of cosecant is 1 over cosecant times the derivative of cosecant. All right, so here is my velocity vector. 1 comma, the cosecants cancel and leave me with minus cotangent t. This lets me write down speed. One plus cotangent squared under that radical is cosecant squared. So I have the square root of cosecant squared t. And just for a moment, I'm going to say that's the absolute value of cosecant t, because that's all I really know. Take the square root of a square, it comes out as positive. But then I remember that I'm dealing with a specific interval of t, and between 0 and pi, cosecant is always positive, so I can erase those, right, and just have cosecant of t there as my speed function. This lets me write down the unit tangent vector, big T. Well, that's convenient because in part B, I'm supposed to write down the frenet frame. I'm supposed to write down big T, big N, and big B, and I already have T written down here. 1 over cosecant is sine. Here I have a minus cotangent over cosecant, so that's a minus cotangent times sine. Well, cotangent is cosine over sine, so I would lose the sign on the bottom and just end up with a minus cosine. And there's big T, and now I can take the derivative of big T. And I have dt dt. I need to know the magnitude of this vector. Well, that's cosine squared plus sine squared, which is 1. That was a unit vector. Well, that's nice. Because when I divide this vector by its own magnitude, I get the normal vector, which I'm asked for in part B, but I already know it's cosine t comma sine t. Also, this is clearly a unit vector, right? That's clearly a point on the unit circle. But I needed this so that I could calculate kappa. Kappa of t. For every moment in time, 1 over the speed. Speed was cosecant. 1 over cosecant is sine times 1. All right, kappa, the curvature for every moment is just sine of t. All right, t just between 0 and pi, and so I can actually think about what the sine function does. Curvature is going to start off small because sine of 0 is 0. I'm not allowed to plug that in, but if I did, it would be 0. And then sine goes up to 1 at pi halves and then back down. Right, so the curvature is going to increase to a maximum curvature at the top and then decrease again. Whatever this graph is, there's a moment at pi halves where it's as curvy as it can possibly be. All right, part B wants t, n, and b. Well, we already know t and n. All right, so B. Well, I know how to find B. I find the cross product of t and n. But this is a plane curve, right? And I don't know what it looks like, but I'm just going to draw a make-believe plane curve and imagine the x and y axes are in the board here. So here's my plane curve. And t and n, always in the xy plane, right? Because I can imagine these plane vectors as having a comma 0 for the k component. And I claim that right now I know at every value for t, there are only two options for the binormal vector. The binormal vector is a cross product between t and n. So it either points straight out of the board in the k direction, or it points straight below the board in the minus k direction. So I'm thinking that at every moment in time, my binormal vector is either plus or minus k. Maybe depending on the moment in time. And those are the only two options for plane curves, right? Because the binormal vector is either sticking straight out or pointing straight through the xy plane. But let's take our cross product and see which it is. So I set up a determinant. This determinant is going to have a row of zeros in it, which is very nice. It's going to make the first two components really easy. So 0 in the I direction. Cover up the middle column, and I get 0 in the j direction. And then I cover up the final column, and I get sine squared plus cosine squared is k. And so now I know for every moment in time, the binormal vector is always k. Okay, big T is pointing in the direction of motion. Big N is pointing inwards on a turn, and it tells me their relationship is always so that k points up and out of the board and never below the board. That gives me some instinct onto how this curve is going to look when I finally do graph it. All right, next up, we have a definition. Let R of t be a position vector. Okay, we have that. The center of an oscillating circle is called the center of curvature. Oh, I'm reading the wrong problem. I should edit that out, but I'm not going to. That's number 3. Number 2. The circle that lies in the oscillating plane of the curve, all right, that's the plane determined by t and n, at a point P, and it has a tangent line that's the same as the curve at P, lies on the side of the curve n does, and has a radius of 1 over the curvature is called the oscillating circle. Let's find the oscillating circle at t equals pi halves. Well, I read through that kind of quickly, and there's actually a typo on that piece of paper. I left out the word same, tangent line. But let's imagine a curve in the plane, and a point on that curve P. Big T points in the direction of motion, and big N's pointing inwards to the turn. What I want to do is I want to find a circle that has exactly the same curvature at that moment P. Well, if you think back to our lesson on curvature in circles, if I draw a circle, its curvature was 1 over the radius. And so its radius is 1 over the curvature. And so if I measure the curvature of this curve, and then I imagine finding its reciprocal, that would tell me the radius of a circle that would have the same curvature. Now, if I plot a point that is this distance away, following this direction in, that would tell me a center of a circle that touches exactly that point with exactly the right curvature. Because now I could take a compass, set it at the radius, and actually just sweep out a circle that has the right amount of curvature. Near that point, the circle I've drawn very crudely and badly there would look a lot like my curve in the way a tangent line looks like a function. This does one step better and matches how bendy the curve is at that moment. So our job now is to find the center of curvature and draw that oscillating circle. So first off, all right, so P is a point on the curve. The center point is in the normal direction at a distance of 1 over the curvature, and everything's happening at pi halves. In part A, we're just asked to find the point on the curve at pi halves. Well, that's what the original position vector does. So I'm looking for r of pi halves. Well, my position vector was r of t is t, comma, the natural log of the cosecant of t. Pi halves, comma, the cosecant of pi halves is 1 and the natural log of 1 is 0. So the point P is pi halves comma 0. That's the point that's going to be on my curve. Okay, and I found a vector that points at that point, but when I wrote down my answer, I wrote it down as a point because I was asked for a point, not a vector. I was asked to calculate that point P. Looking at the center of the oscillating circle, this point should be rho units away from P in the direction of big N. Well, I know P. And now let's find big N at pi halves. Well, big N, the principal unit normal vector, was the vector cosine t comma sine t. So that's that nice happy point on the unit circle. Evaluating cosine and sine at pi halves gives me the vector 0, 1. Rho of pi halves, 1 over the curvature. Well, the curvature is sine, so 1 over the curvature, sine of pi halves on the bottom. I'm just going to get out 1. The curvature is 1, the radius is 1, right? Because 1 is its own reciprocal. And so now I'm supposed to find the center of curvature. The point on my curve is at pi halves 0. It is 1 unit away in the direction of the normal vector. So, the normal vector says start at your point, don't go left or right at all, go 1 unit up. Well, that is 1 unit away. There's my center of curvature, right at the end of my normal vector. If the radius had said 2, I would need to go up 2 units. If it said 1/2, I need to scale back down. But this is the nice, easy case where my normal vector has exactly the right length just to point to the center of curvature. So the center of curvature would be the point, pi halves, and then 1 unit above would just give me that 1. The next part asks me to find the equation of the oscillating circle at this moment in time. Well, it has a center of pi halves, it has a radius of 1. That circle's not too hard to write down. X minus pi over 2 all squared plus y minus 1 all squared equals the radius squared. There's my circle. And then we're asked to use a graphing calculator or GeoGebra to graph r of t. And so linked in the YouTube description of this video and on our Moodle course page, you'll actually see a GeoGebra graph with both things on it. But this morning I thought it would be helpful to actually use my TI-83 because we always have access to those. And so we need to make sure by hitting the mode button that we're in the radian mode and using the parametric mode. Because every vector equation is really hiding parametric equations for my points. So our original vector equation here, right, telling me an x-coordinate and a y-coordinate for every moment in time. So now I'm going to hit the y equals button, and I need to type in this vector equation. So I use the variable button, and there's the x equation is t, and then the natural log of 1 over sine. I'm going to hit the window button because I want to make sure I'm graphing this between 0 and pi. And I'm just going to hit zoom 6 so it looks just like yours probably will. And I see it curving around it and doing that. And I could zoom in on that, and I could change the window, do all kinds of crazy things. I'm going to zoom in close to that center of curvature. All right, and there's what my curve looks like. Because t is between 0 and pi, I'm going to imagine that it actually continues this shape approaching those asymptotes. And when I graph it on my board, it would look something like this. Trying to do this somewhat to scale. Here's the point pi halves 0 that's on my graph. And I can see that my curve has asymptotic behavior because t never gets to be 0, right? I start just, 0 is not included in my interval, and neither is pi. GeoGebra does a really good job of graphing this. And there I have the direction of motion too, because as t goes from 0 to pi, I'm definitely moving that way. All right, my center of curvature was this point, and that lets me sketch in a circle just by imagining points 1 unit away in every direction. And the whole point of this circle is that really close to that point, we have the same curvature and they look similar. Here's a graph I did a little earlier with a little more detail. All right, now here is question number 3, which I unfortunately started to read a moment ago. So let R of t be a position function. The center of an oscillating circle is called the center of curvature. The plane curve C, formed by the set of all of the centers of curvature of R, is called the evolute of R. And then we're asked to express the x and y coordinates of the oscillating circle's center for R as functions on t. What we've done here is we found one center, right? And now the idea is that every moment in t, I have a point on this curve that should correspond to some center of curvature. So the centers of curvature themselves should have some kind of vector formula, some set of parametric equations to generate them. So now it's our job to see if we can track those down. Well, let's just think about our curve for a moment. If I take a point on that curve, big T points in the direction of motion and big N points inward towards the curve. My center of curvature lies somewhere along this path. The flatter my curve is, the further away my center of curvature has to be because of that reciprocal relationship between the curvature in a circle and its radius. And so this is pretty flat, so I think my center has to be pretty far away over there. And so I need some way of thinking about how to calculate that point. Well, R of t is a vector that points to the point on the curve. Points to a point on the curve. And then I want to think about a vector that points from that point to that point that's a center of curvature. Well, it's not the normal vector at t itself, but it's the normal vector, which is a unit vector, with a distance multiplied it, that rho of t, right? Because a vector is its direction multiplied by its length. And if I look at these two pictures, this is a vector and then another vector drawn from its head, the resultant vector, the sum of them, is exactly what I'm looking for. This sum, which I'm going to call q of t, is a vector function that points at the center of curvature. And so all I have to do is take what I know already from what I have written down on other boards and write this new vector function q down. R of t is t, comma, the natural log of cosecant t. Rho was the scalar function sine t. And then big N is cosine t, comma, sine t. Excuse me, rho was cosecant, 1 over sine t. Sorry, the curvature was sine, rho is its reciprocal, and I should have looked in my notes instead of trying to do that from memory. So take that lesson from me. So this is a vector function that points at the center of curvature. Let's simplify it. 1 over sine times cosine would be cotangent of t. Add the I components and I get t plus cotangent t. Comma, 1 over sine t times sine t would be 1, so add the j components and I get the natural log of cosecant t plus 1. So the two equations I'm looking for are an x equation and a y equation. Those parametric equations trace out my oscillating circle's centers for every value of t. So I'm going to go back to my TI-83 and I'm going to type those in to x2 and y2. So t plus cotangent of t, so cosine over sine. And then the y equation, the natural log of cosecant, which is 1 over sine, plus 1. And there's that point that we had already plotted at pi halves comma 1, and now I know that the rest of the centers of curvature trace out a shape that looks like this. So again, remember taking this point here, big N points perpendicular to the curve, 1 unit. And going that direction, I should get some point on this green curve. And apparently, with where I picked that point this time, this would have to keep going out for a ways until I got to that center of curvature. That is the evolute of my curve given by these parametric equations. Okay, so that's all of the problems I had posted for summarizing the material of this week, but I did one more this morning in class, so I wanted to do it during this video too. Wasn't sure we'd have enough time, so I left it out, but one of the other topics from this week was talking about the acceleration vector and how that we can always express the acceleration vector as a linear combination of big T and big N, where a sub t is the tangential component of acceleration, and big N, a sub n is the normal component of acceleration. And there are two different formulas for that. The one I've seen students use and use myself more often is this one that comes from the Pythagorean theorem, which is going to make me calculate the acceleration vector and then take away what I find here. All right, so our first job is to calculate the derivative of speed. And unfortunately, we've already written speed down for our example here. Speed, the magnitude of velocity, was cosecant of t. So a sub t, its derivative is minus cosecant t, cotangent t. Now we need to find the normal component of acceleration, which means I need to write down the actual acceleration vector. I'm going to start with my position vector. We've already found velocity, but I could imagine just taking a derivative again, but it was 1 comma minus cotangent t. And now I just need to take a derivative again. The derivative of cotangent is minus cosecant squared, so with that minus out front, it becomes a positive cosecant squared. And right away, the magnitude of acceleration is really easy to calculate. It's cosecant squared t. Right? 0 squared plus this squared, take a square root, and I get back to cosecant squared t. So now I have this and I have this, so I can imagine using that formula. Don't have to imagine it, I can actually use it. Got a square cosecant squared, so that's a cosecant to the 4th, minus square this, and I get cosecant squared t cotangent squared t. I can factor out a cosecant squared and take the square root. I'll just get cosecant. And again, I should pause for a moment and think, hey, that could be an absolute value, but I know I'm between 0 and pi, so everything works out fine. Then under the radical, I'm left with cosecant squared t minus cotangent squared t. Nicely enough, there's a Pythagorean identity that says that's equal to 1. So here is my acceleration vector, written down in this format. As soon as I erase a spot to write it down. Okay, so my acceleration vector, written as a linear combination of big T and big N. The tangential component was minus cosecant t cotangent t, big T, plus cosecant t, big N. And there's my acceleration vector written down in that format. One of the mistakes I've seen students make is instead of using symbols for big T and big N, they want to plug in the vectors. You can do that, and then you distribute, you get back to the original acceleration vector that we wrote down. And that's not a bad way of checking your answer if you have a lot of time, But if you're just trying to write down the acceleration vector in this way, we use big T and big N in symbolic form.